In this video, we're going to look at questions 10 and 11 from the Calculus BC Chapter 9 practice test. And here we're going to determine which of these functions grow at a faster rate. And for number 10, we've got natural log of x and the cube root of x. For these problems, I always like to say that you should have some kind of an idea about which of these grows faster before you even attempt the problem. So taking a look at this, I got a natural log function. I've got a cube root function, and the general rule of thumb is that the natural log function is going to grow slower than any power function. So that's the assumption I'm going to start off with, and I want that assumption because then I only have to think about the theorem about growth rates in one particular way. So let's see, the limit as x approaches infinity, and we're going to do the slower function on top and the faster function on the denominator. And if this does go to 0, then we did prove that the function on the denominator grows faster than the function on the numerator. So let's check. This should be an indeterminate form. Let's see. The limit as x approaches infinity of the natural log of x, yeah, that's equal to infinity. And the limit as x approaches infinity of x to the 1/3 power, that also grows without bound. So this is indeterminate, and we can use L'Hopital's rule. So let's use L'Hopital's rule. And the derivative of the natural log of x is 1 over x. And the derivative of x to the 1/3 power, well, that's 1/3 x to the negative 2/3 power, which is 1 over 3 x to the 2/3 power. That simplifies to the limit as x approaches infinity of 3 x to the 2/3 over x, which further simplifies to 3 over x to the 1/3 power. Now the numerator is staying constant and the denominator is growing without bound, so this limit is equal to 0. So since the limit of the ratio goes to 0, that means whatever function's on the denominator is going to grow faster. So therefore, g of x, which was the cube root of x, grows faster than f of x, which was natural log of x. We're going to do the same process, but now with question 11, we've got x and 1 over 1 plus x. And let's talk about this one because it looks as though this second function here has a little something extra added to it. Otherwise, these two functions are exactly the same. So it seems as though the x plus 1 over x should grow faster. And let's check that with a limit. Okay, we have the limit as x approaches a very sloppy infinity of x over x plus 1 over x. And we're going to check to see, is this actually indeterminate? And yeah, the numerator grows without bound. And the denominator as well grows without bound. So we're safe to use L'Hopital's rule. That gets us the limit as x approaches infinity of 1 over 1 minus 1 over x squared. Let's simplify that. And I simplified this, but then I realized I'm doing something really dumb. We don't need to do all of this because we know that 1 over x squared as x approaches 0, or as x approaches infinity, this is going to approach 0. So the limit is just 1 over 1 minus 0, or just 1. And since we got a constant here, x and x plus 1 over x, they both grow at the same rate. And further, what that says to me is as x approaches very, very large numbers, this part of it, the 1 over x, that is really insignificant when compared to x. Which should make a little bit of sense because 1 over x, that limit is going to be equal to 0 as x goes to infinity. So eventually, these two functions are going to be basically the same function for large values of x. So this was a short one comparing the relative speeds of function, and we'll see you for our next video on the Chapter 9 practice test. Have a good one.